guys, today we're going to do another video and we will speak about the electron configuration.
The electron configuration is important because it tells us about the way and the behavior of the atoms, and it also tells us about the way that atoms bond each other and how the molecules are grouped.
Every atom has electrons, and these electrons orbit the atomic nucleus. The electrons are not found at the same distance from the nucleus, but they can be found in certain zones around the center of the atom. This zone is called orbital, and they are of four types: S, P, D, F. Every single orbital has its own characteristics. Each orbital has its own form. The orbital S has a spheric form. The orbital P has a two lobes form. The orbital D has 4. The orbital F has 6. The period table is divided also upon the type most often orbital. The elements of the first and second principal groups have their most often orbitals of type S. Those from the third to eighth principal groups have as most often orbitals. Groups are divided in transition metals and latanides and actinides. These first have their own orbitals in D, the second on type F. To define better the characteristics of the electrons, I used quantum number. The principal quantum number is indicated with n, refers to the distance of the orbitals from the nucleus. Moreover, this number indicates the energetic level that goes from 1 to 7. Theoretically, it goes even above, but until now aren't found elements with an even higher level, but they cannot have 0, because this means that electrons would be found in the nucleus, which would be impossible. The orbital quantum number is indicated with L, and is calculated L equal n minus 1. For L equal to 0 as S orbital, for L equal to 1 orbital P, for L equal to 2 as D, for L equal to 3 as an F orbital. The magnetic quantum number indicates the direction of the vector of an electron in presence of an electric camp. This is indicated with ML, and it can have a value from minus L to plus L. The quantum number of spin refers to the verse of a rotation of an electron around its axis. It can assume values from 1/2, minus 1/2 and plus 1/2. When it is positive, it rotates counterclockwise. When it's negative, clockwise. If we wanted to find the number of electrons present in an atom, we should observe two properties: the atomic number and the charge. The atomic number indicates the protons, but also the number of electrons. So, the carbon, which has atomic number 6, it will have 6 electrons. If instead we had an ion with a positive or negative charge, for example sodium ion, that has 11 electrons, but because it has a positive charge, it means that it has lost an electron. We have to remember that the electrons are what moves from atom to atom, and not the protons, which are bound to the neutrons. That's why the number of protons cannot vary. If we had chlorine, in this case chlorine has 17 electrons and it gains 1 electron, so it has 18 electrons. We said the electrons are put around the zone around the nucleus, called orbitals. Let's go and do the configurations of some elements, like lithium, oxygen, titanium and cerium. Electron configuration is described as the illustrative method which allows us to represent the way in which electrons are put in an atom or in an ion. We indicate orbital with squares. Each electron is indicated with an arrow. Arrow up means positive spin, arrow down negative spin. And if we had to put 2 electrons in the same square, they should be of opposite spin. In every single square can be put at maximum 2 electrons. Let's start with lithium. Since the electrons are ordered according to the kinetic energy, so that it is always increasing. So we can proceed firstly giving priority to energetic levels 1, 2, 3, 4, etc. and then two sublevels SPDF. The atomic number of lithium is 3, so it has 3 electrons to distribute. Each orbital has an energetic level that can go from 1 to 7. We feel firstly the orbital 1s of energetic level 1. It is filled with the first 2 electrons and there remains 1. At the next level there is the orbital 25, the 2s, which has more energy. But there are also orbital 2p, which have even more energy. That's why we fill firstly the orbitals of lower energetic level and we put an electron in the orbital 2s. The electron configuration will be 1s2, 2s1. If we take oxygen and apply the same method, we can observe that it has 8 electrons, from which some in the orbital 2p. Let's fill the various orbitals until we arrive to the orbital 2p. Since when we are filling orbitals we need to try to maintain a repulsive index as low as possible between electrons, we will fill the orbitals putting every single electron in an empty orbital, in a way that the electron is unpaired. And after we fill all present orbitals, we will pair the electrons of opposite spin. At the end becomes 1s2, 2s2, 2p4. Now we can see an element which has orbital of type d. In this case, the 3d orbitals have such a high energy that they exceed that of 4s orbitals. From the diagram we can remember the order to fix the electrons. The configuration of titanium, the element with the orbital d, is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Another element that has f orbitals is cerium. It has a lot of electrons, 58 precisely, and has a configuration
1 2s2, s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 4f1, 5s2, 5p6, 5d1, 6s2,
of which we can see that it has 1 electron in the orbital f. The electronic configuration follows the same method also for very big atoms. If there is an ion, for example chloride, means that it has gained an electron and we will have the same configuration of argon.
Okay guys, this process is really complex in some way. In fact, it has many peculiarities that we won't discuss about them, but we treat only in a general way the electron configuration.
Okay guys, if you like this video, like it, share it, comment and subscribe to the channel.
Thanks for watching.